Imagine a robot trying to catch a falling glass. Its camera sees the glass slipping off the table, right? But its internal brain takes like 200 milliseconds to imagine the future video frames of that falling glass before it can even calculate how to move its arm.
And I mean, by the time the processor actually outputs the motor commands, the glass is already shattered on the floor.
Exactly. Welcome to AI Paperslop. Today, you and I are analyzing a paper that solves this exact latency bottleneck. It's called GigaWorld-Policy-0.5, a faster and stronger WAM empowered by AutoResearch by Giga AI and Tsinghua University.
Yeah, and the core insight here is that world action models, or WAMs, normally suffer from massive inference latency because generating future video tokens for robotic control is just computationally overwhelming.
Right, but this paper solves that by decoupling training and inference using an action-centered mixture of transformers architecture. It uses future visual dynamics for dense physical grounding during training, but then it just entirely skips video decoding at inference.
Right, so by using a lightweight action expert paired with a custom native C++ runtime, the architecture achieves this blistering 85 millisecond latency on a local consumer-grade RTX 4090 GPU.
Which is insane. It outperforms heavy-hitting baselines like Pi 0.5 and fast WAM in both raw computational speed and, actual real-world task success rates.
It really does.
So the goal for our analysis today is to unpack the specific architecture, the flow matching setup, and the automated training pipeline that actually makes this edge deployment performance possible.
Yeah, and to really understand the significance of that 85 millisecond latency, we have to look at the fundamental problem with how most modern robotic foundation models are trained. The dominant paradigm right now is the Visual Language Action Model, or VLA.
Right, where the mathematical supervision is just incredibly sparse.
Exactly. You feed the neural network an image of the environment and a text prompt, and the model learns to output the exact motor torques or joint angles that a human demonstrator used in the training data.
So it's essentially doing high-dimensional behavioral cloning.
Yeah, it learns to mimic the human's hand movements, but it doesn't necessarily build a causal understanding of the physical consequence of that movement.
Yeah.
A VLA doesn't natively know that dropping a glass causes it to shatter.
Right.
It just knows that when the pixels look a certain way, the gripper state should change to open.
Which is exactly the gap that world action models attempt to bridge. Because instead of just mimicking the action, WAMs jointly model the actions and the future visual observations.
Right.
The network is forced to predict not just the immediate joint angle, but how the entire scene will physically evolve over time.
And that future scene evolution acts as this incredibly dense supervision signal. I mean, it forces the internal weights in the model to learn a physically grounded representation of reality.
But then you hit a massive deployment bottleneck.
Oh, yeah.
Because that joint modeling process is brilliant for the training phase. But in previous WAM architectures, you were forced to invoke that exact same heavy generation process during inference. You had to explicitly roll out those future video tokens to get the action tokens.
Which is, iterative denoising on a sequence of future video frames is agonizingly slow. You just cannot use it for real-time, closed-loop robotic control.
Because by the time the robot mathematically imagines the future, the physical present has already shifted.
Exactly. And furthermore, if the model hallucinates or, introduces slight errors into those imagined future visual frames, those visual errors accumulate over long time horizons.
Right. And that accumulated noise feeds back into the autoregressive loop and completely wrecks the downstream action generation, causing the robot to just drift off course.
Yeah, so the elegant fix here stems from the original GigaWorld policy architecture, which introduced this concept of action-centered causal token masking.
Okay, so in a standard transformer, attention matrices allow tokens to look at each other to build context. But here, they mathematically structure the attention matrix so that future visual tokens are allowed to attend to the action token.
Right, meaning the model's imagined future is strictly conditioned on the specific actions the robot is actually taking.
But they place a strict causal mask that prevents the action tokens from attending to the future visual tokens.
Exactly. The causal masking mechanism severs the dependency in one direction. The action tokens are predicted purely from the current visual observation, the current robot proprioceptive state, and the language instruction.
So they are mathematically isolated from the future visual tokens.
Yes. And because the generation of the action token doesn't require the future visual tokens to be computed first, you can simply omit the future video generation entirely during physical deployment.
It is remarkably similar to the process of learning to drive a car.
Oh, how so?
Like during training, when you're a teenager in driving school, the instructor forces you to explicitly visualize and articulate the future consequences of every movement. Like, if I turn the wheel left here, I will cross into the oncoming lane and the car behind me will have to slam on its brakes.
Right, you're forced to think through the whole sequence.
Exactly. You're generating this mental movie that's your dense visual supervision.
Mm-hmm.
But at inference, when you're just driving to work on a Tuesday morning, you don't consciously sit there and render a high-definition mental simulation of the future before every single micro-adjustment of your steering wheel.
You just react.
Right. You react and steer instinctively based on deeply ingrained physical priors. And this causal masking architecture does the exact same thing. It trains with the heavy mental movie, but it infers on pure, rapid instinct.
Yeah, and those physical priors are baked directly into the network's weights during the gradient descent phase of training. But to push that efficiency even further, version 0.5 completely upgrades the backbone to physically separate the visual and action modeling into distinct neural pathways.
This is their mixture of transformers architecture, right?
Yes, exactly. Rather than using a monolithic, fully shared backbone for every single token, the workload is split. So the model features a massive visual expert and a significantly smaller, lightweight action expert.
And these two experts remain connected through multimodal self-attention layers, but they just handle different data streams.
Right.
And the visual expert does the heavy lifting, processing the dense visual tokens generated by a WAM VAE encoder.
Which is crucial because for those dealing with raw pixel data, the WAM VAE compresses raw high-resolution images into a compact latent space.
Yeah, because feeding raw pixels into a transformer would completely choke the attention mechanism, since compute scales quadratically with sequence length.
Exactly. And this massive visual expert is initialized from the pre-trained GigaWorld-1 world model.
And when we say massive, we're talking about a 3072 hidden dimension and a 19336 dimension for the feed-forward network.
It's huge.
Right.
But the action expert is dedicated entirely to action token denoising. And to create this expert, the researchers initialized it directly from the visual expert's weights.
So that transfer allows the action expert to inherit the robust physical priors learned by the world model.
Right. However, to make it suitable for low latency inference, they deliberately truncated it. They basically extracted the leading submatrices of the visual expert's weights, mathematically shrinking the action expert down to a much leaner 124 hidden dimension and a 4096 feed-forward network dimension.
If we look closely at the terminology here, calling this a mixture of transformers or a mixture of experts might actually confuse some ML engineers listening.
Oh, because in the context of large language models, a mixture of experts usually implies dynamic token routing.
Yeah. A small routing network evaluates each token on the fly and dynamically decides which expert gets which token based on its semantic content. If that were happening here, it would introduce extra computational overhead. But looking at the paper, this is actually static modality-specific routing, isn't it?
It is entirely static. Visual tokens are hard-coded to flow through the visual expert, and action tokens are hard-coded to flow through the action expert. There's no dynamic router network evaluating the tokens.
Okay, that makes sense.
Yeah, the mixture simply refers to the fact that they have specialized heterogeneous transformer blocks processing fundamentally different data modalities within the same overarching sequence.
But wait, if they are adding specialized experts and technically increasing the overall parameter count of the complete architecture compared to a single shared backbone, how are they physically bypassing the heavy visual generation during inference to actually speed up the model?
Well, the speedup is unlocked by combining that modality-specific routing with the causal masking we discussed earlier.
Right.
During real-world deployment, the network simply does not receive or attempt to predict future video tokens. Because the massive visual expert is strictly responsible for visual tokens, it only fires to encode the single current visual observation from the robot's cameras at the very start of the time step.
Oh, wow. So once that current state is encoded, the visual expert is completely bypassed.
Exactly. The lightweight action expert just takes over, rapidly denoising the action token step after step.
So by dropping the future visual tokens from the sequence, you're effectively amputating the most computationally expensive part of the network during the active high-frequency control loop.
Yes.
That is a massive computational shortcut. I mean, it leverages the heavy parameters for world understanding during training, but computationally amputated them when the robot actually needs to move fast.
Right. And to squeeze every possible millisecond of performance out of this severed architecture, they rely on a highly specific mathematical framework and a hardcore edge inference stack.
Yeah. Right. The whole model is optimized using flow matching, which maps a simple distribution, like pure Gaussian noise, to the complex ground truth data distribution by regressing a vector field.
Yeah, but what really stands out is how they independently handle the noise scheduling for the different modalities. Action tokens and visual tokens represent fundamentally different mathematical realities.
So they require completely different denoising trajectories.
Exactly. Flow matching utilizes modality-specific flow time steps to address this. They apply different shift factors. Let's denote them as gamma A for the action tokens and gamma V for the visual tokens.
Because, denoising visual pixels is roughly analogous to resolving spatial frequencies to sharpen a blurry photograph.
Right.
But denoising joint angles, however, is like fine-tuning the continuous physical trajectory of a steering wheel, because these represent different types of mathematical corrections. Forcing them onto the exact same noise schedule creates a convergence bottleneck.
Exactly. So by decoupling those shift factors, the algorithm independently controls the noise scheduling. They linearly interpolate between the Gaussian noise and the ground truth data to regress the target velocity field.
Optimizing the denoising path for the robot's joints differently than it optimizes the path for the camera's pixels.
Yeah, but a brilliant mathematical formulation on a whiteboard won't hit an 85 millisecond latency on a physical robot.
Right. This is where the deployment stack comes in. The engineering optimizations are what actually translate that math into hardware reality, and they utilize KV caching extensively.
They do, because during the autoregressive action generation loop, the language instruction given to the robot, like pick up the apple, does not change.
So the language prompt is processed exactly once by the MT5 text encoder, which yields the necessary token embeddings.
Right, and KV caching saves the mathematical states, the attention keys and values of those text embeddings, as well as the encoded state of the initial visual observation.
So if the robot takes 500 iterative steps to move its arm toward the apple, recalculating the attention matrices for the phrase pick up the apple 500 times is just a massive waste of FLOPS.
Exactly. The KV cache allows the model to fetch those pre-computed states from memory, drastically reducing redundant computation.
And to push the hardware further, they utilize torch compile for aggressive operator fusion.
Yeah, modern GPUs have incredible compute power, but moving data back and forth from the high bandwidth memory to the CUDO's cores takes time.
So torch compile analyzes the inference graph and fuses multiple mathematical operations into single CUDO kernels. The data just stays in the fast SRAM on the chip for multiple steps before being written back to main memory, which heavily minimizes memory bandwidth bottlenecks.
Right, but the ultimate speed unlock here, and this is a critical takeaway for anyone trying to deploy embodied AI, was building a native C++ runtime.
This is so important because Python is the standard for AI research, but it is notoriously problematic for real-time robotics.
Oh, absolutely. Python relies on the Global Interpreter Lock, or GIL, and utilizes automated garbage collection.
Right, and a garbage collection pause of 20 milliseconds might go completely unnoticed in a web server application. But if a robotic arm is swinging a payload next to a human worker, a 20 millisecond latency jitter is a critical safety failure.
So the researchers built a C++ middleware integration that strips out the Python dependency entirely.
Wow. And that C++ runtime orchestrates the entire pipeline natively. It handles the image pre-processing directly from the hardware cameras, manages the tensor construction, maintains the KV cache memory blocks, executes the optimized model, and processes the final action outputs.
And latency drop is staggering. When running this model on a massive server-grade A100 GPU using standard Python, the latency was 189 milliseconds.
Okay.
When they moved it to an RTX 4090, a consumer GPU that you can physically bolt onto a mobile robot chassis, the Python latency dropped to 110 milliseconds.
Still in Python, though.
Right. But by deploying that native C++ runtime, they slammed the latency down to 85 milliseconds on that same 4090.
Which is incredible. 85 milliseconds translates to the robot adjusting its physical trajectory roughly 12 times every single second.
Yeah, and operating at 12 hertz provides the high-frequency reactive control necessary for complex manipulation tasks.
But raw speed is useless if the policy itself isn't highly accurate.
True. And the accuracy of GigaWorld-Policy 0.5 is heavily dependent on a massive, highly automated training recipe.
Right. The pre-training phase utilized 2,000 hours of open-source robot data. And this wasn't just a narrow, single-task dataset. It included massive, multi-embodiment datasets like RDT-1B and Attribot.
Because training on diverse multi-embodiment data is non-negotiable for world models. The network has to learn to generalize across completely different lighting conditions, camera angles, and underlying robotic kinematics.
But they didn't just run standard WAM training on this data, did they?
No, they used a mixed pre-training strategy that combined standard world action modeling with action conditioned world modeling, or ACWM.
Because standard world modeling often just forces the network to predict how a scene evolves passively, almost like watching a movie.
Right, but ACWM explicitly forces the network to predict the future visual evolution conditioned specifically on the robot's own actions.
So it creates a hard causal link. The model learns that the environment is not just changing randomly, but changing as a direct consequence of the motor torques it outputs.
Exactly. And the ablations in the paper demonstrate how critical this causal link is. The mixed training strategy achieved an 85% success rate on evaluation tasks, remarkably fast.
Oh, wow.
Yeah, in contrast, standard training without that explicit action conditioning only managed to hit a 75% success rate, even after 50,000 training steps.
But what's wild is that optimizing the hyperparameters for that mixed training strategy wasn't even done by a human.
Oh, right.
They utilized Andrej Karpathy's AutoResearch pipeline. Instead of having a machine learning engineer manually tweak learning rates and babysit tensor board graphs for weeks, they basically unleashed an automated AI agent to sweep for the best configurations.
Yeah, the agent executed a series of cheap 1,000-step pilot runs to test different setups. And during these pilot sweeps, they evaluated a learning rate of 3E5 against a higher learning rate of 6E5.
Okay, and what happened?
Well, the 3E5 learning rate actually produced a better visual loss, meaning it was better at predicting the exact pixel layout of the future frames.
Interesting.
However, the 6E5 learning rate produced a better action loss, yielding a 0.252 error rate compared to 0.257 for the lower learning rate.
Which highlights the core advantage of defining a rigorous algorithmic goal. Because, if a human engineer were just scanning the overall loss metrics, they might have selected the lower learning rate because the visual predictions look cleaner.
Right.
But the AutoResearch agent was explicitly programmed to prioritize action loss. It recognized that for a robotic control policy, the mathematical quality of the motor output is fundamentally more critical than rendering a pixel-perfect imaginary video.
Exactly. So the automated pipeline correctly ignored the slightly blurrier visual predictions, selected the 6E5 learning rate paired with the batch size of 16, and then automatically committed the massive compute budget to scale that winning configuration up into a full 30,000-step extended run.
It functions exactly like an algorithmic trading firm. Like a quantitative hedge fund doesn't just guess where the market is going. It runs rapid, cheap, low-risk pilot algorithms to hunt for a specific market signal.
Right.
And once the automated system identifies a signal that yields the exact metric it cares about, it ruthlessly executes the massive trade. The AutoResearch pipeline applies that exact same empirical automation to hyperparameter tuning.
Yeah, it's brilliant. And that optimized server-side math translates directly to the physical world. The researchers proved this by evaluating the trained policy on the Agilex Piper 6 degree of freedom robotic arm.
Okay, let's get into the evaluations.
So they ran exhaustive tests on both short horizon text following tasks and highly complex long horizon tasks. In the text following category, they tasked the robot with fruit picking and object placement.
How did it do?
Well, GigaWorld-Policy 0.5 achieved a 0.85 success rate on fruit picking and a 0.89 success rate on object placement, comfortably beating baselines like Pi 0.5 and Modus.
The object placement tasks are particularly revealing because they require really fine-grained spatial grounding.
Oh, absolutely.
Because instructing a robot to place a fork into a basket requires a vastly different geometric understanding than instructing it to place a bowl on a flat plate. The model must visually ground the identity of the object in its gripper, identify the 3D destination, and comprehend the specific spatial relationship dictated by the preposition in the text prompt.
Right. And beating the Modus baseline by a 6% absolute margin on these compositional spatial tasks proves that the massive visual expert successfully transferred an incredibly nuanced 3D understanding of the physical environment down into the lightweight action expert.
So the action expert inherited the spatial geometry required to manipulate the environment. But picking up a fork and dropping it into a basket is a relatively short, contained action.
Yeah, it's a short horizon.
Right. And the ultimate stress test for any robotic control policy is executing multi-step operations continuously without failing. Which brings us to the long horizon tasks, specifically food heating and tableware arrangement.
Yeah.
And I want to emphasize the significance here. On these complex multi-step tasks, GigaWorld-Policy 0.5 achieved a 0.80 success rate. To put that 0.80 in perspective, the absolute strongest baselines tested were completely falling apart, hovering between a 0.50 and 0.60 success rate.
Wow.
This new architecture delivered a massive 33% relative improvement over the state of the art, because in robotics, long horizon tasks are the ultimate acid test because of the physics of compounding errors.
Right, the covariate shift problem.
Exactly. Let's look at covariate shift. At time step 0, the robot is executing an action perfectly aligned with the training data. At time step 1, it makes a tiny 1-degree error in its joint angle. It's barely noticeable. But by time step 10, the arm has drifted 5 inches away from where any human demonstrator ever positioned it in the training set.
Right, and because the arm is in a novel physical location, the robot's cameras are now viewing the environment from an angle that literally does not exist in the training distribution.
Exactly.
So the model experiences a covariate shift. Up, it's a completely erroneous action based on the unfamiliar visual input, and the errors just compound exponentially until the robot crashes the gripper into the microwave door.
But the fact that this architecture maintains an 80% success rate across these long sequences proves that the temporal priors learned from the heavy visual expert are functioning as a robust state space attractor.
Yeah, the action expert isn't just blindly reacting to the current pixels. It possesses a deep, stable understanding of the sequence of physical states.
Right, so when the arm gets slightly perturbed off its trajectory, that baked-in physical understanding pulls the arm back to the correct path, preventing the cascading failures that normally destroy standard VLAs.
The dense visual supervision required during the training phase basically acts as an invisible stabilizing force during inference. The model essentially understands the physics of the task so deeply that it can course correct on the fly without needing to explicitly generate the future visual frames to verify its assumptions.
Which entirely resolves the historical tension in embodied AI. Previously, you either used a massive model to get deep physical understanding but sacrificed real-time reaction speed, or you used a tiny model to get low latency but sacrificed complex physical reasoning.
Right.
This paper proves we can have both. We can utilize the profound, dense physical understanding of world models during training, but then computationally amputate the expensive visual generation modules at inference, resulting in VLA-level speeds with WAM-level stability.
It really is a huge step forward.
Which leaves you with a critical engineering question to explore. If we can successfully sever the visual foresight module at inference for robotics without losing those deep physical priors, what other modalities in AI could we train jointly for deep supervision, only to computationally amputate them at deployment for hyper-efficient edge models? Could this train-heavy, amputate-for-edge methodology become the new universal standard for all embodied AI?